discuss the next topic in the chapter phase equilibria. The topic is Gibbs phase rule. This Gibbs phase rule was given by the scientist Willard Gibbs in the year of 1874. At that time, chemist does not realize its importance, but later on, when the applications of Gibbs phase rule was studied, at that time they feel it is one of the important rule given by the Gibbs. Now, what it is? If an equilibrium is there in the heterogeneous system and that equilibrium is influenced by the external parameters like temperature, pressure and composition, then the relationship between degree of freedom, number of components, number of phases is given by the equation called as Gibbs phase rule. In fact, Gibbs phase rule is a mathematical equation. So, if an equilibrium in a heterogeneous system is influenced by parameters like temperature, pressure and concentration. At that time, the relation between degree of freedom, number of components and number of phases is given by the equation called as Gibbs phase rule. Now, what is that equation? That equation is F is equal to C minus P plus 2, where C is nothing but where F is nothing but degree of freedom, C is nothing but number of components, and P is nothing but number of phases, while 2 is constant. So, this mathematical equation itself is a Gibbs phase rule. This also may be written simply as F plus P is equal to C plus 2. This is another way to write the equation. It doesn't make a difference. Now, where the terms are, F is nothing but degree of freedom, C is nothing but number of components, P is nothing but number of phases, and 2 is nothing but constant, or 2 is constant in the equation. So, this is what this equation called as Gibbs phase rule. Now, we see the details of the terms phases, degree of freedom and number of component one by one, and how they are calculated when we have a heterogeneous system. So, first we see what is the meaning of phase and how to calculate the number of phases. Now, the important term in the Gibbs phase rule is phase or phases. The Greek meaning of the phase is nothing but appearance. The Greek word appearance is also recognized as a phase. Now, what is phase? It is a physically distinct, chemically homogeneous and mechanically separable part of the system called as a phase. It is physically distinct, chemically homogeneous, and mechanically separable part of a system called as a phase. Now we see how to calculate phases. Okay, before to that, we'll see the meaning of each term. Physically distinct means these phases have a definite bounding surface. When they have a definite bounding surface, then they are physically distinct, physically separable. Another one, they are mechanically separable. Means we can separate them mechanically. There is a boundary of separation. We can easily define boundary of separation between the two phases that we can easily identify. Another one is, yes, the mechanically separable means simple processes like filtration, decantation, hand picking, separation by using separating funnel. If we carry out the separation by using these methods, then we say that it is mechanically separable. But it does not include the processes like evaporation, distillation. Remember this. We cannot carry out these processes. Another one is absorption. So, only separation by mechanical processes like filtration, decantation, hand picking, separation by using separating funnel, but not processes like evaporation, distillation, absorption, or the extraction. Then we say that it is a phase. Now we discuss some examples and we'll try to find out the number of phases in the system. For example, suppose that we have a mixture of gases. The best example is air, which contains N2O2, CO2, carbon monoxide, N2 in gaseous state, O2 in gaseous state, CO2 in gaseous state. We cannot justify the difference in between them. We cannot say yes, this is N2, we cannot say this is CO2, we cannot have a boundary of separation between them. And hence all are homogeneous. So phase is one. Remember this. All are having a single phase. Now we see another example. Now another example is miscible liquids. We have many examples of miscible liquids in our laboratory. For example, water plus acetic acid, water plus alcohol, benzene and CCl4. So all these are miscible liquids and they are homogeneous, so all are having single phase, and that is a liquid. So these are the examples of the single phase system. Another one is all pure substances. Remember this. All pure substances are also in same phase, single phase. So this is the example. Now we see one more example. Suppose that if ice is in contact with liquid water. So ice is in solid state, water is in liquid state. So we have two phases. Remember this. Suppose that water is in contact with water vapor. Water is in liquid state while water vapor is in gaseous state. So we have two phases. One more example, we'll see. If we have two immiscible liquids, one is organic and other one is inorganic. So at that time, the two immiscible liquids also gives us two phases. For example, water and CCl. Remember, both are in liquid state, but we can separate out them by using separating panel. There is a boundary of separation in between them, and hence though both are in liquid state, but till we have two different phases. One is water and other one is oil phase, or the carbon tetrachloride phase we say. One more example. In the same case we'll see, and that is suppose that if we have water, carbon tetrachloride and mercury. So in this case we have three different states. One is of H2, which is liquid, carbon tetrachloride liquid, and mercury is also separated. So we have three phases. So this is an example which is having three phases. Now another example we'll see of saturated solution. Suppose that a small amount of salt is added. Let's consider HCl plus water. So what will happen? A small amount of HCl remains at the bottom, and hence we have two phases. One is liquid and other one is solid. So we have a solid KCl as well as KCl in water. So in case of the saturated solution, we have two phases. And if we'll take unsaturated solution, at that time we have only homogeneous solution and phase is only one. So the unsaturated solution of any salt, single salt, we have a single phase, while the saturated solution we have two different phases. Now another example we'll see, mixture of solids. If the solids are different, then whatever the number of solids, that much number of phases we will calculate. Mixture of solids. Remember this, number of solids is equal to number of phases. We have an example for that case, decomposition of calcium carbonate. We'll heat calcium carbonate, we'll get calcium oxide and CO2 gas. Now in this example, we have two solid phases and one gas phase, and in total there are three phases. This is solid, and this is gas. So two in solid form and one is gaseous phase, and both are separable. So two phases in the solid and one phase is in gas, and total in the system there are three phases. Okay, we'll stop here, and in the next video we'll see the details of the remaining terms.